अच्छा ये स्टार्ट कर लेते हैं. We talk about secondary halogenoalkanes. Last time कल हमने क्या किया था कि we did nucleophilic substitution. I told you that there are three nucleophiles that do this substitution thing. You've got OH -1, you've got NH3, they've got lone pairs, and you've got Cn -1. So you've got three nucleophiles, three different conditions, and you have nucleophilic substitution. And the first one was that I told you that that when you have a primary halogenoalkane, so what happens in a primary halogenoalkane is, let's say, so what happens in a primary halogenoalkane is that the carbon has a pretty strong positive charge because it's not surrounded by large groups. So it's not going to form a carbocation because the positive charge would be so strong that the Cl -1 will not leave it. I mean, the carbon positive would be so strong that it would be pulling those electrons back. It won't allow the Cl to escape. So it's an unstable carbocation. So carbocations are not going to be formed. So instead, if you want to get rid of these electrons, you want to push them away towards Cl, the nucleophile must attack it. There's a strong positive charge over here, and the nucleophile is going to come in, and its lone pairs are going to get attracted. They're going to come in, and the electrons over here are going to get repelled, and eventually the Cl -1 will break off. So in this case, you need a nucleophile to push the Cl away. But in the other case, in a tertiary halogenoalkane, the carbocation is really stable because even if it gets a positive charge, the positive charge is going to be very weak. It's going to have a low charge density because the positive charge is surrounded by large groups with lots of electrons. So those electrons can be pulled towards that, and the positive charge can be partially neutralized, which is why the charge density is not very high. So the positive carbon atom is not very positive in the first place. So it's not really interested in those electrons. It can get electrons from other places. It's surrounded by so many electrons. So the Cl, if it wants to pull these electrons, the carbon over here will not be pulling those electrons back. So it's a very stable carbocation. It's got a lesser positive charge density, surrounded by alkyl chains which have an electron donating effect. So in this case, the nucleophile comes in the second step. The Cl -1 leaves first, and a carbocation is formed, which is very stable. And then the OH -1 comes in, and that's how the reaction mechanism happens. And we discussed everything about why we call it 1 and why we call it 2. Let's talk about secondary halogenoalkanes. Secondary halogenoalkanes are kind of something that's in between. They follow, depending on conditions, both Sn1 and Sn2 mechanisms are followed. But depending on conditions. So it all depends on conditions. A secondary halogenoalkane is this thing. It's got a CH3. I mean, it's got two carbon chains. It's, the carbon over here in the middle will have two carbon chains of varying sizes, and there's going to be an H and a Cl. Now, the positive charge is kind of in between over here. It's a polar bond, but over here the carbon is surrounded by only two electron donating groups, and on one side there's an H. So the positive charge is kind of in between. So depending on condition, maybe it forms a carbocation. Let's say you got very high temperatures, so the molecules are really bumping into each other. So the chances of forming the carbocation would kind of increase. The chance of the CCl bond breaking off would increase maybe if the temperature is really high. And then the OH -1 or any nucleophile would come in and would bond with it. The other one is it can also follow It can also follow the Sn2 mechanism. Maybe the temperature is very low, or maybe the nucleophile concentration is really high. So what can happen is that there's a positive Cl, not the Cl is negative. So there's a slight negative Cl and a slight positive carbon atom. And you'll have a nucleophile. And maybe the concentration of the nucleophile is really high. So the nucleophile comes in first, attacks the carbon, and the electrons over here, they get repelled, leading to a transition state, which would look like this, that there's going to be a CH3 carbon with another CH3 and an H. And over here, there's going to be Cl leaving, and the OH or the nucleophile would be joining in. So it depends. It depends pretty much on the conditions of whatever the conditions are. ठीक है, is this clear? Alicia, Hania, is this clear? Abdullah, clear?
Yes, but sir, what kind of conditions?
If, for example, if the OH ion concentration is really high, maybe the OH ion comes in and attacks the carbon and the Cl gets knocked out. Maybe the temperature is really high and there's a very bright chance of the CCl bond breaking during those collisions. So it's kind of in the middle. So you can't really predict which mechanism would be followed by secondary halogenoalkanes. Okay. Alicia, is this clear?
Yes, sir. Thank you.
So it can follow both mechanisms. But remember, the reason for the differentiation in the mechanisms, like in the tertiary halogenoalkane, the carbocation was very stable because you got a lot of carbon chains. So the positive charge was kind of very weak, which is why the Cl can easily leave with its electrons. But in the primary, the positive carbocation that should be formed is not going to form because the positive charge on this would be very strong because it's not surrounded by large groups. So the Cl would not be able to leave on its own. So the OH must come in to push the Cl away. So secondary halogenoalkanes are kind of in the middle of the two. So the stability of the carbocation is kind of in the middle. So anyways, we're going to talk about the stereochemistry of the two mechanisms. Okay, this is something that's also very important. So stereochemistry of the mechanisms. By stereochemistry, I basically mean I'm talking about optical isomers. So we're talking about optical isomers. Recently, they have actually asked you questions on this. So we are dealing with optical isomers. If you have the Sn2 mechanism, and if you remember this properly, optical isomers are mirror images. Like you'll have a carbon atom, and there's going to be you'll have a carbon atom, and that carbon atom will be bonded to 4 different groups. Let's say it's W, X, Y, and Z. Then there's another version of the molecule which is going to be a mirrored version of the same molecule, and in that mirrored version, just like your two hands, which would look very similar, but they're going to be inherently different. And so there's going to be a carbon atom with 1 bond on top. The dotted bond would be over here. 1 bond coming out of the page, and there's going to be 1. So these are 2 mirror images of each other. So W stays on top. Z is now pointing on the left. Y is over here, and X is over here. So those are stereoisomers, optical isomers to be specific. And you have a chiral carbon atom. Now let's talk about the mechanism. what happens to the mechanism when you have Sn. Let's talk about Sn1 first. We're talking about the Sn2 mechanism. So let's talk about the Sn2 mechanism. Now let's assume here's a chiral carbon atom. And it's a halogenoalkane. I'm drawing the three-dimensional image of this molecule. So remember, when carbon is bonded to 4 atoms, it's tetrahedral. So that's a tetrahedral carbon atom. And let's say there's this secondary halogenoalkane, and it's chiral as well. So all 4 groups are different. And there is an H over here and a Cl on this side. So this is exactly the same as, I'm just drawing a 3-dimensional picture of the molecule. Otherwise, the mechanism is exactly the same. Remember, in the previous case, we weren't dealing with the 3-dimensional. I mean, this wasn't the actual shape of the molecule, like the one that you see over here. This one over here. This wasn't the actual shape. Carbon, when it's bonded to 4 atoms, it's tetrahedral. So the only difference I've done is I'm actually using the correct 3-dimensional picture of the molecule. Now, so I'm going to draw the same mechanism. The CCl bond is polar. Carbon is positive and Cl is slight negative. There's going to be an OH minus 1 that would come in. The OH minus 1 will be attracted to the carbon positive, and this is the Sn2 mechanism. So the electrons over here are going to be repelled, and the OH minus 1 is going to get attracted to this carbon, which is positive. So what will happen? What's going to happen is that the OH comes along. Just a second. 1 second. So what's going to happen is that the Cl over here will get knocked out, and the OH would come from this side and bond with it. So what will happen is I'm going to draw the transition state now. The transition state is going to look like this. If I can draw a good 3-dimensional image. So the ones in the red, nothing would happen to them. The Cl would be getting knocked out from one side. So the Cl is getting pushed away, and the OH is coming from this side. So that's how initially it's going to look like. Let me just draw this. So focus on this carbon atom that's right in the middle. Forget the ones that I'm circling at the moment. The ones in red. You've got a CH3, you've got an H, you got a CH3, CH2. So I'm ignoring those for a second. And let's just focus on this carbon atom. There's an OH that's coming in from one side and the Cl that's getting knocked out from the other side. So the carbon atom is right in the middle. What will happen to the other bonds? The other bonds would look like this, that there's going to be a CH3 on top. So there's going to be a CH3 on the top. There's going to be an H, and let's say this is your CH3, CH2, and you'll have NH over here. So that's our second step. What's going to happen is when the OH minus one comes from this side, attacks from this side, all these other bonds, they're going to get knocked towards the other side. I mean, this CH3 will get pushed to the side, this H will get pushed to the side, this would also get pushed to the other side. Because remember, the OH negative charge over here is going to, it's not only going to repel the Cl, it's going to repel everything. Everything is going to get pushed to the other side. So the OH minus one is coming from the left side. So not only is the Cl getting pushed away, but all the other bonds are kind of getting pushed away. So the last part would be that the Cl would eventually break off. Cl would eventually get knocked out by the OH minus one that's coming in. And the very last part is going to look like this, that you'll have a carbon over here and the OH will eventually form a bond. And all these other bonds are going to get repelled to the other side. So you'll have a CH3, you'll have an H, and you'll have a CH2, CH3. And the Cl is eventually going to get removed. It will get knocked out. So that is what is happening. I'm just drawing a slow motion picture of what's happening in 3-dimensional. So you had a tetrahedral carbon atom, which was chiral. There was a Cl, which was slight negative on this side. The OH minus one came in, attacked the carbon positive from the other side because this is negative, this is also negative. So the OH minus one is going to come in from the other side. Now the OH would start joining in with the carbon atoms. The Cl is going to get repelled, but not only Cl. I said not only Cl. Just hold on 1 second. Sorry. So you have the Cl over here, the OH minus one is coming in, the OH starts bonding with it, the Cl gets knocked out, and eventually what would happen is that the OH will bond, but all the other bonds are going to get pushed to the other side. So this particular molecule is going to be formed. Is this 3-dimensional diagram clear? Yes or no? Anya, is this clear, Abdullah,
Yes.
Alicia?
Yes, sir.
I said now the point I'm trying to make is that you'll only get just one chiral in this case, not the other one. Because remember when you have optical isomers, in the other molecule, like for example, if you look at Z's bonded to the right, over here Z's bonded to the left. So the point I'm trying to make is that in the Sn2 mechanism, you only get one optical isomer. Why? Because the OH minus one would always be coming from the left side. If the Cl is on the right side, the OH minus one would always be coming from the left side. So the OH minus one would always be bonding to this side. I mean, you're not going to get this molecule. You're not going to get the mirrored version. What's the mirrored version of this molecule? Remember, this can form optical isomers. It's got 4 different groups. So it can form mirrored versions, just like your 2 hands. But the other one will not exist. I mean, the other one, if you mirror this, the other one would look like this. The OH would be on the right side. The H would be instead pointing in this direction, coming out of the page. You'll have CH2, CH3 over here, and you'll have a CH3 over here. So the other mirrored version, where the left to right is laterally inverted. Okay, just like your 2 hands, there's a CH3 on the top. And there's a CH2 CH3 over here. The other molecule is not going to exist because the OH minus one would always be attacking from one side. So this molecule over here is not going to exist. It's not going to form. So you'll only get one version of the optical isomer.
Sir,
Yes.
I don't understand why we only get one version.
For the other version, the OH must be coming from the right side, right?
Yeah.
So the point is that if the Cl is over here, and this is the side which has negative charge, I mean, it's got slight negative charge, the OH minus one would always be attacking from this side, from one side. Do you get my point? So the OH minus one would always be bonding from on the left side. So the other mirrored version,
Sir,
yes.
but what if the OH ion, it
Huh.
attacks the optical isomer of the initial one, the initial halogenoalkane?
This one?
Yeah, the optical isomer for this. What if OH attacks?
Obviously it's going to form the other one. Then it's definitely going to form the other one. I'm just saying if you have this optical isomer and the OH minus one reacts with it, it's always going to form just one optical isomer, one version of the optical isomer, not the other one. If there was the other optical isomer, then it would form the other one. Okay,
Thank you.
so the point is, you only get only one optical isomer formed, not the other one. Hanya, is this clear?
Yes, sir.
It's going to become
So
even.
there's no like major product and minor product in this.
Yeah, it's something like that. Exactly something like that. I mean, you don't call it major and minor product, but it's something similar to that. Now we're gonna do the case of Sn1 mechanism. There you'll see that both isomers would be possible. So let's do the Sn1 mechanism. Now remember, in the Sn1 mechanism, the mechanism is different. Remember secondary halogenoalkanes. This was a secondary halogenoalkanes. They can undergo both types of mechanisms depending on condition. So where was the secondary? So when you have the Sn1 mechanism, the carbocation is formed first. I mean, the OH minus one doesn't attack. The OH minus one comes in later, once the carbocation has already formed and the Cl has already left. That's when the OH minus one shows up. So the mechanism is different. So let's draw the three-dimensional diagram of this. I'm gonna do the same thing. Like the first part would be exactly the same, except for the fact that there's not going to be any OH minus one. Okay, the Cl would leave first. So I'm going to keep everything the same, except that there is no OH initially. So the Cl leaves. When the Cl leaves, you're left. Remember, when the Cl leaves, what's going to happen? A carbocation would be formed. So the Cl has left with its electrons, and this carbon will become positively charged. And ignore the Cl. It took all the electrons in the bond. It became -1, right? Took both electrons. Now that's gone. So when carbon is only bonded to 3 atoms, what type of shape does it have? When it's only bonded to 3, it's only making 3 bonds. It's fan shaped. So I'm going to draw the correct 3-dimensional shape of this molecule. It's not going to look like this. I mean, the Cl has left, taken its electrons with it. So carbon only has a bond over here, a bond over here, and a bond on this side. So it's just got 3 bonds. So when it's got 3 bonds, the actual shape of the molecule would look like this. It's going to be fan shaped. So I'm going to draw this over here, that the actual shape of the molecule would look like this. There's going to be a carbon atom, and there's just like a fan that's lying on the side. So that's how the carbon would look like. It will have an H. So it's going to have an H, and it will have a CH3 and a CH2 branch, and it's going to have the CH3 on one side, and the middle carbon would be positively charged. So this is how the carbon, the shape around the carbon atom would kind of look like when it's only bonded to 3. The Cl is left, it's only bonded to 3 atoms. Is this point clear?
Yes, sir.
Hania, is this clear? Abdullah, is this clear? Nabila?
Yes, sir.
So now the thing is, I mean, I'm going to delete this. This was just for understanding this, that the Cl left. So you're left with just 3 bonds. So the molecule would actually look like this. So this is how the molecule would look like this. I'm just going to ignore the Cl as well, because that's gone. So let's put it somewhere on the side. So that's gone now. Now the carbocation, I mean, all the carbocations that we drew, this is the 3-dimensional shape of the carbocation. Like we drew the carbocations over here. This wasn't the 3-dimensional shape of the molecule. This was just the structural formula. This is how the carbocation would actually, in reality, look like. It's going to look like this in 3 dimensions. Now, in the second step, once a carbocation has been formed, now the OH-1 would come in. Now, think of a fan. This is like a fan, and the middle carbon is positively charged. Now, the OH-1 has 2 options. It can either come in from the top and bring its electrons and bond from the top. That's one option. The other option is that, imagine this as a fan. The other option is that it can come in and not come from the top, but the bottom. Take it from underneath the fan. So that's your second option. So the OH-1 will bring its electrons, but this time it's going to bring it and join from the bottom. So now you've got 2 options, because remember, this is I mean, the fan is a symmetrical shape. It's not like in the previous case you didn't have a choice. In the previous case, the OH-1 was attacking initially, so it wasn't able to attack from this side. It always had to come from the other side, which is why you always got one version of the optical isomer. But now, in this case, if the Sn1 mechanism is followed and a carbocation is formed, the carbocation is a symmetrical shape. I mean, the OH-1 has choices. It can attack from the top, or it can attack from the bottom. Both are possible. So if it joins from the top, what would it look like? You'll have a carbon atom. The OH will bond from the top. So that's where the OH is bonding from. And all the other bonds are going to be pushed downwards. So the H would get pushed downwards, the CH3 will get pushed downwards. So all the other bonds are going to get pushed downwards. So that's your CH3. CH2, this is your H, and this is your CH3. So that is one. So that's one optical isomer that's going to form. The other one is going to be the mirrored version. The OH will bond from the bottom. So I'll do everything the same. You'll have a carbon atom, and the OH is going to bond or attach itself from underneath the fan. And all the other bonds are going to get repelled upwards. So there's a CH3. Here's your H. And there's CH2, CH3. So you have CH3, you've got H, and you've got a CH2, CH3. Okay, let me just. Anyway, so the whole point is now two different optical isomers can be formed. They're both mirrored versions of each other. I mean, you can put a mirror underneath, they're just reflected versions of each other. So in this case, if the Sn1 mechanism was followed, the OH-1 had two choices. Like the OH-1 came in after a carbocation has been formed. And because of the shape of the carbocation, it's a symmetrical molecule. The OH-1 could attach from the top. It could also attach from the bottom. So two different mirrored versions are possible in this case. Is this clear?
Yes, sir.
So you're going to write about this, that the trigonal planar, it's a fan-shaped molecule which is called trigonal planar carbocation. You're going to talk about it if they ask you for the reason, and they have asked you for the reasons in the recent papers. So you've got a trigonal planar carbocation, and nucleophile can attack from the top or from the bottom. So the nucleophile, whatever the nucleophile is, there are three nucleophiles, OH, CN, or NH3. So it can attach from the top or the bottom. And two optical isomers are possible, and there's an equal possibility of the two optical isomers. And they might ask you to actually draw the two optical isomers as well. So you have to, because recently these questions have been asked. Most of the questions in the past papers, you wouldn't get this, but recently this has been asked from you about the chirality of the molecules, and this is something that's related to drug synthesis, which is that it's kind of difficult to actually, I mean, you have to choose your reaction pathways very carefully, whether you want the Sn1 or the Sn2 mechanisms, because remember both optical isomers are not going to behave exactly the same way. Like if you're making a drug molecule, a medicine molecule, one of them would be useful, the other one would have side effects, which is why you have side effects from medicine. So when you're deciding on making a molecule, you're probably not going to prefer the Sn1 mechanism, because the Sn1 mechanism leads to both types of chirality. If one of them is going to be good, the other one would be bad. You'll actually prefer the Sn2 mechanism, because in that case, at least you'll be pretty sure what type of optical isomer you're getting. You only get one type of optical isomers. So in that case, if you're designing the reaction pathway, I mean, they're not going to go into a lot of detail, just the general idea of why Sn2 would probably be better than Sn1. Is this clear?
Yes, sir.
Yes, sir.
So, and that's pretty much it about Sn1, Sn2 mechanisms. Here, this last part was just tricky. They've just recently asked things about it. So just keep this in mind. Now, the other thing is about halogenoalkanes. So we're done with Sn1, Sn2 mechanisms. The other thing about halogenoalkanes is, I mean, not actually done. I just had to write a few more points on this. Just hold on one second. So I'm just going to write about the significance of this reaction where the nucleophile is Cn minus 1. There's a certain significance of this reaction, and that is that that when you attach a Cn and the Cl gets knocked out and the Cn, the carbon chain length increases. So remember this, that this reaction is kind of really useful in increasing the carbon chain length. You don't have a lot of reactions where carbon chain length actually increases. Like you had two, I mean, over here you had 2 carbons, over here you also have 2 carbons. So that's, I mean, most reactions, the carbon chain length does not increase. But if you wanted to increase the carbon chain length, then this was your go-to reaction. That's the reaction that you're going to do if you want to increase the length of the carbon chain. Another thing that you should be careful about is the elimination reaction, which is that there's a reaction which is very similar to this. You add NaOH and reflux and heat, but instead of aqueous, you use concentrated NaOH. So that's known as an elimination reaction. You don't need to know the mechanism. So what's the elimination reaction? It's so this one is, you have a halogenoalkane. So here's a Cl, and the rest are all H atoms. Now in the elimination reaction, the Cl is lost and the H is lost from the neighboring carbon atom. So it could be this one or it could be that one. So you're going to get 2 different molecules in this case. Alkenes are formed. So 2 different molecules are going to be formed. So everything remains kind of the same, except that 2 of the atoms kind of get eliminated. So the Cl is lost and the H is lost from the neighboring carbon atom, and instead in the middle you get a double bond. And the same thing kind of happens over here. The Cl is lost and the H is lost from the carbon on the left, and in the middle you get a double bond. So you're going to get 2 alkenes. That's it. That's elimination. This one will have cis and trans. There would be two versions of this, because it fulfills the cis and trans stereoisomers conditions. There's a double bond and both sides are different. Both sides over here are different. Different groups are attached on this carbon atom, different groups are attached on this carbon atom. The condition for this reaction is very similar to substitution, except that you use NaOH, which is ethanolic. And it's concentrated as well. Plus you're going to heat this. So if you use NaOH aqueous, you get substitution, you get Sn1, Sn2 mechanisms. But if you use NaOH and ethanol is the solvent, and you heat it, you get an elimination reaction. So this is another halogenoalkane reaction that you should remember. So here, let's continue in the next class then, TK. We'll try and cover carbonyl compounds quickly, and we'll try and be done with this, TK. So any questions? All clear?
All clear.
Okay, take care. Allah Hafiz.
Allah Hafiz. Thank you.
Allah Hafiz.